Hello everyone, I am Nikhil Garg and I will present the paper titled Signal to Spike for Neuromorphic Regulated Reservoir Computing and EMG Hand Gesture Recognition. In this presentation, we would first talk about motivation and EMG datasets. Then we will talk about spike encoding, baseline and evaluation. Then we move on to reservoir computing pipeline, reservoir topology and activity regulation. Towards the end, we would discuss the results, conclusion, and future scope for the study. So hand gesture recognition using EMG signals can be used to control prosthetic arm. These gesture recognizing AI algorithms are difficult to be implemented on portable devices due to their limited power budget. Brain-inspired algorithm or neuromorphic algorithm, which require lesser power, requires efficient representation and computation of information in form of spikes. We use two open source EMG-based hand gesture recognition dataset for our study. These are collected from Mayo armband, which is composed of 8 channels and a sampling rate of 200 Hz. The first dataset, which is a Rochambeau dataset, is composed of 3 gestures, rock, paper, and scissor, collected across 10 participants with 3 sessions per participant. The second dataset, which is a sensor fusion dataset, is composed of 5 gestures collected across 21 participants, with each participant took part in 3 sessions. A segment of 200 milliseconds collected from the 8 channels of the Mayo armband is represented here in the graph. The raw EMG segment is converted to spikes with help of spike encoding algorithm. The threshold of this encoding algorithm is optimized through the baseline evaluation pipeline. We compute the difference between amplitude of subsequent samples. A spike occurs if the difference exceeds either the positive threshold or negative threshold. Hence, we obtain 8 channels of spike trains for both up and down polarity. We then combine the up and down channels and compute rate vectors through a non-overlapping window of 200 milliseconds. These rate vectors are then used to train a LDA or SVM based classifier for gesture classification. The encoding parameters, which are VTHP and VTHN, are optimized for classifier performance. The key takeaways from the encoding pipeline is that the spike encoding is an important step in neuromorphic computing pipeline, and it is crucial to ensure that important information for class separation is preserved. It is also important to evaluate the efficiency of encoding before passing the information to an SNN. This is to establish a baseline for comparing different SNN topologies and plasticity mechanisms. We then feed the spike encoded segments to our reservoir computing pipeline. Reservoir are a class of neural networks called recurrent neural networks, which take into account the input from the present time step and the reservoir state from the past time step. We have the 8 up channels and the 8 down spike encoded channels, which we feed into a reservoir of spiking neurons. This is composed of 80% excitatory neurons and 20% inhibitory neurons. The excitatory connections are trained with the help of critical plasticity algorithm. The input topology is a random connectivity with 15% of the reservoir synapses. Hence, for a reservoir of 320 neurons, we have 174 input synapses and 1161 recurrent synapses. For reading out the reservoir states, we compute the mean firing rate across a sliding window of 200 milliseconds. These rate vectors are then fed into the SVM or LDA-based classifier to compute the 5 gestures or the 3 gestures in case of Rochambeau dataset. We then talk about the reservoir topology and activity regulation algorithm. The spiking neurons are organized as a small word topology composed of macro columns and mini columns. Excitatory and inhibitory connection across macro columns and mini columns are depicted in respective color. Each neuron is modeled as an adaptive leaky integrated and fired neuron. The activity regulation is done with the help of critical synaptic plasticity algorithm. The branching factor is the number of spikes generated in the postsynaptic neuron as a result of single presynaptic spike. If the branching factor is less than 1, the activity of the reservoir dies with time, while if the branching factor is greater than 1, the activity explodes. For a branching factor of 1, we see a regulation in the reservoir activity and an optimal state. The critical synaptic plasticity algorithm drives the reservoir weights to the branching factor of 1. We then present the result of classification for Rochambeau dataset and sensor fusion dataset. We report the threefold cross-validation accuracy in form of mean and standard deviation for our methods and method reported in past studies. We obtain 85.4% of accuracy for spike encoding and evaluation baseline, and we obtain 81.83% of accuracy for reservoir with fixed weight and 88% for reservoir with critical plasticity algorithm. We notice that the spike encoding and evaluation baseline performs better than the reported studies which use the reservoir for computing. We also note that the reservoir with fixed weight performs worse than the spike encoding baseline, and the reservoir with activity regulated with critical plasticity performs the best. For sensor fusion dataset, where we consider only the EMG subset of the entire dataset, we obtain an accuracy of 65% for spike encoding baseline. This is in turn higher than the spiking MLP and CNN reported in the past. For reservoir with critical plasticity, we obtain a performance of 70%, which is higher than the reported CNN and multilayer perceptron figures. Next, we study the dependence of performance on reservoir size for Rochambeau dataset and sensor fusion dataset. We plot the accuracy obtained with critical plasticity for SVM and LDA-based readout in these plots. What we observe is the radial SVM-based readout performs better than the linear discriminant analysis-based readout. Also, the performance increases with the increase in reservoir size for both Rochambeau and sensor fusion dataset. We draw the following conclusion from our study. Readout on spike encoded data is efficient for obtaining optimal encoding parameter and establishing baseline before feeding into subsequent SNNs. The high performance of simple machine learning classifier applied to raw data in absence of any signal processing and feature extraction algorithm validates the proposition of using event-based sensor for measuring biopotential signals. The regulated reservoir of spiking neurons operating with a branching factor equal to 1 performs better than the state-of-the-art CNNs, which further validates reservoir computing applicability for processing time series data, while operating at the edge of chaos. In real-world deployment, essentially, a null class should be presented to avoid the actuator command in resting state. Therefore, in future, we plan to incorporate more gestures along with the resting state command. Thank you everyone for listening. I would end this presentation with acknowledging our funding sources and looking forward to meet you at the conference.